Okay, so continuing off on these climate global tipping points in the Earth system, I'm talking about specific ones that are in the U.S. Climate Report, the recent U.S. Climate Report, and we're talking about it's talking about the potential for carbon release from the Arctic. A warming Arctic, we risk greatly, having catastrophic release of carbon, either from the permafrost or from the ocean sediment clathrate, greatly rocketing us up to a much warmer world. Nothing new normal about the present situation. We're only scratching the surface on extreme weather events, etc. This will be a cakewalk compared to what's coming down the pipes if we get this huge carbon emission from the Arctic. The ice sheets and sea level rise. The Antarctic and Greenland ice sheets are clear tipping elements. Okay, warming of 1.6 degrees C above pre-industrial, we're almost there, could commit Greenland, so it's basically committed now to 85% reduction in ice volume and 6 meter or 20 foot sea level rise over millennia. Okay, now the RCP 8.5 shows complete loss of Greenland ice sheet. Now, forget about the 6,000 years, okay? There's all kinds of things that are happening that are speeding up the melting of ice, and also that's like this is ridiculous time frames to talk about. It should really be talking about how the rate of melt from Greenland and Antarctica is doubling every 7 years, and has been doing this for 3 or 4 doubling periods, and how if it continues to do those, the sea level could rise 7 meters by 2070. Just Google that and watch the videos that I've done on that. Antarctica, this would be the amount of ice that sits on bedrock below sea level. So the part that's most vulnerable is we're talking 23 meter sea level rise. Okay, various ice dynamics are going on. A study just came out recently on calving of ice on the edge of the ice sheets, and how that is a lot quicker and a lot worse than we think. There's also volcanoes underneath the ice, so as some of the ice melts and the pressures relieve, these volcanoes could go off and basically cut like a scythe right through the ice. The RCP 8.5 scenario, we could get a meter or more the remainder of this century just from Antarctica alone. Even faster is in many papers. 2 degrees Celsius or 3.6 is sustained warming, 25 meters of global sea level rise from Antarctica alone. Okay, now ecosystems, there's huge tipping points in ecosystems, right? The boreal forest will expand as the temperature rises, but the forests are darker. So when if they're replacing the lighter tundra, then they're absorbing more solar radiation, can cause some regional warming. The coral reef ecosystems, the Brazilian rainforests, etc. Okay, habitat. As temperature, as conditions shift on the surface of the Earth, then the habitat that is required for species to survive gets decimated, gets hammered, and species can either migrate quickly or die. A lot of them can't move that fast or migrate, so they go extinct, and extinctions are way, way up. So now looking at the Paleo Climate, looking at the deep climate records in the past, what other surprises can we see? Okay, so there's 3 periods that are talked about here. They're all well before Homo sapiens appeared, about 200,000 years ago. I think the most recent number is 300,000 years ago. We found some more fossils, so we've been around for a bit longer. We extended our lifetime on the planet by about a third, 100,000 years. Okay, so the late Pliocene, 3.6 to 2.6 million years ago. Okay, when climate models try to model this period, they underestimate the warming north of 30 degrees. Okay, during the middle Miocene, 17 to 14.5 million years ago, the models also, they underestimate the temperature above pre-industrial, and they also there was a 40% reduction in the pole to equator temperature gradient compared to today. So the jet streams were much weaker and very, very different. Okay, so the models don't pick up on this. And also in the Eocene, 56 to 48 million years ago, no permanent land ice, CO2 concentrations peaked about 1,400 parts per million, global temperatures 14 degrees Celsius warmer, which is 25 degrees Fahrenheit warmer. And there was about half, the pole to equator temperature gradient was about half of what it is today. And the models don't catch this. Okay? So why don't they catch it? Okay? So one possible idea is that there was a planetary state shift. Okay? So some of the models show that at higher CO2 levels, one modeling study suggests an abrupt change in atmospheric circulation. And this is the onset of this equatorial atmospheric superrotation. Okay, between 1120 and 2240 ppm of CO2. Okay, so what happened is the air circulation at the equator changed completely. There was less moisture carried from the equator to higher latitudes, so there was less clouds. So it approximately doubled the climate sensitivity. Okay, in that case. So in other words, the climate would warm at double the rate that it would warm at now because of this changing for a given amount of CO2 increase. But the critical threshold for this transition is poorly constrained. If it happened in the past at a lower CO2 level, it might explain the Eocene discrepancy, maybe the Miocene discrepancy. So it could be, if that was true, then it could be a plausible threat within the 21st century under the higher RCP 8.5 scenario. Okay, so I'm going to talk about that a bit more, but let's just finish. So basically, there's lots of surprises that are not captured in the climate models. So we're at huge risk of passing tipping points in the Earth system, rocketing us up to a new state, severely threatening the global food supply, the ability to get fresh water, right? Huge geopolitical conflict would arise, and there's even scientists that are talking about the potential for human extinction. Not, if we rocket up 4 degrees, how do we survive on this planet? How do any of us survive? And we're living in caves or nuclear submarines, but forget the civilization, forget most of the planet. Okay, so let's talk about this. What is equatorial planetary superrotation? Okay, so this happens on Venus. So superrotation means that the winds aloft, the winds at high altitude at the equator, are faster than the planet's rotation. So the planet's rotating and the winds at the surface are faster. So how does that possibly happen? It's like stirring a cup of coffee and then noticing that the coffee is actually turning faster than your spoon's turning. That's the idea of this superrotation. Okay, so what you do is if you go to Google Images, go to Google Images, or select Images, and put equatorial planetary superrotation. And this is a good explanation here. So yeah, so the wind speeds at the equator are faster than the surface speed. It's expected away from the equator to conserve angular momentum, like a zonal jet. Superrotation, so you need a mechanism to make the winds go faster at the equator. You need momentum transferred to those winds, and there's possible mechanisms here. Now, I went into, here's the circulation that we have right now. So the equator is the hottest, we get air rising and condensing, you get the clouds there, you get the intertropical convergence zone, then the winds spread out, both in the north, this is in the northern hemisphere, also in the southern hemisphere, and they cool down and they descend and you get a gear. So you get the descending air is very dry, this is where the world's deserts are. Then you get that's the Hadley cell rotation, then you get the Ferrel cell, like a gear, this is 60 degrees, and then you get the polar cell, and here's where you have the subtropical jet and the polar jet. So as the temperature gradient, you need that temperature gradient to set these up. cold Arctic, warm equator. As the North Pole temperature goes up, this whole level moves up, and the jet streams become much wavier and are affected more by the land. So this is what happens now. Now what happens if you warm the equator too much? You get the rising, and you can get totally different patterns without the Hadley cell occurring. So I'll just bring up two particular papers here. I'll look at this here. So this is happening, this super rotating, in the direction of rotation, prograde equatorial jets are in, Jupiter and Saturn both have it, Venus and Titan don't. Okay, so it does exist on some other planets. Now, what I want to show you, I'm not going to go into the details of these papers. These are all, you can access these but just by Googling. But in one of the more exotic behaviors exhibited by simplified atmospheric general circulation models is a transition from a conventional general circulation, right, where we have westerly mid-latitude jet streams. This is the case that I showed you here in this diagram. Okay, so what can happen is that if you get a warm enough equator, then it can break this pattern. Okay, if you get a warm enough equator, and if the friction at the surface is low enough, and if the warming is all around the equator so that you don't have large baroclinicity or large pressure gradients, so you don't have large temperature differences. The whole thing is hot and it extends out from the equator, so there's not large temperature differences. Then you can get this phenomena, this super rotation, equatorial super rotation. Okay, the math gets pretty complicated. Let's just have a look. You can look at some of the figures and some of the what happens, the diagrams and so on. But what happens is, if there's if there's a lot of heating at the equator, and if it's hemispherically symmetric, then what happens is the air, you could get air that is, you get very, very hot equator, very, very rapid rise, very, very huge and strong convection. That pulls air in from lower latitudes, but it's very, very hot air, so that builds up, and you can get this, basically the winds go faster, so the Earth is rotating, the winds go faster than the rotation, and you get much, much less ability of air to move from the to higher latitudes. So the equator just gets super hot. People wouldn't be basically living at the equator. If you did have pressure changes and temperature changes, then you could get like a Hadley cell which straddles the equator, both sides of the equator, for example, and you wouldn't get this type of setup. Okay, but basically, this has been studied. Okay, so basically it generally occurs when the heating from below is very, very strong. Okay, the threshold heating at which the transition to super rotation occurs increases as the baroclinicity or the bottom drag increases. So if there's more bottom drag, but at the equator it's mostly ocean, right? So the bottom drag is not great. The baroclinicity, if you get a warming about, to high, say from -10 degree, from 10 degrees south to 10 degree north, warming very, you don't get an abrupt warming and then a cold area, so you don't have this baroclinicity, then you can get this super rotation occurring at the equator. And basically everything is rewired and changes on the Earth system. So this will be an area of very, very intense research, I think. It changes the Rossby waves, it changes the momentum transfers, it changes the ocean currents, it changes the amount of heat, it changes the complete conditions on the surface of the entire planet. So, can we go to a state like this? This would certainly be an abrupt change. And I must admit, I don't know too much about this. This is where planetary scientists who study, Venus and things, these rotations on Venus, they know quite a bit about it. So anyway, I'm sure I'll be doing more videos on this type of phenomena. So the point is we're playing with fire here. We're poking the climate system with a stick, and it's awakened. It's an angry beast. Thank you for listening to my videos.